Hi, this is for Aerospace Engineering Honors, debriefing on homework assignment called Circular Orbits, homework number 4. Number 1, a small moon is in a circular orbit around the planet Cygnus Lenses Beta. It has a mass of 2.36 times 10 to the 25th power kilograms. The orbital radius of the moon is 16,500 kilometers. Calculate the orbital period of the moon and express your final answer in units of minutes. All right, well, so Newton's version of Kepler's third law would be t squared is equal to 4 pi squared r cubed over gm. And in this situation, we don't need to rearrange the equation because we're solving for the orbital period, capital T. So we're going to plug in 2 pi, which is the square root of 4 pi squared. R is 16,500,000 meters because we have to do it in units of meters, not kilometers. That's going to be raised to the third power. To make it cubed, we're dividing by g, which is 6.672 times 10 to the negative 11th newtons meter squared per kilogram squared. And we're dividing it by the mass of 2.36 times 10 to the 25th power kilogram. So, let me set this to where you can actually see what I'm typing in. 2 pi times 16500,000 cubed divided by g, which is stored in calculator memory, divided by 2.36 times 10 to the 25th power. And I forgot I need to take the square root of all that too. So yikes, the square root of this much, but not that much. So maybe I should redo this one. 2 pi square root of 16,500,000 cubed divided by g divided by 2.36 times 10 to the 25th power. And I see that wasn't entered correctly. Let's try this again. Cubed divided by g divided by 2.36 times 10 to the 25th power. Whew. All right. So I get a period t of 10,600 seconds. But it says express your final answer in minutes. So dividing by 60 seconds per minute, the answer is 177 minutes. Number 2, a shuttlecraft orbits Kappa Felix 5. The shuttle has a speed of 2.38 kilometers per second and its orbital radius is 18,200 kilometers. Calculate the mass of Kappa Felix 5. Well, v squared equals gm over r applies in this situation. And we're going to rearrange the equation to solve for the mass of the planet. So the mass of the planet would be v squared times the orbital radius divided by the universal gravitational constant g. So the numbers I'm going to plug into my calculator are 2,380 meters per second squared times 18,200,000 meters divided by the universal gravitational constant g. And it says I have 1.55 times 10 to the 24th power kilograms. Number 3, a satellite orbits Vorta Gamma at an altitude of 640 kilometers above the surface of the planet. The planet has a mass of 3.89 times 10 to the 23rd kilograms and a radius of 3895 kilometers. Calculate the orbital period of the satellite, express your answer in units. So here's the planet. Its planetary radius is given and the altitude is given above the planet. So to come up with the orbital radius, I have to add the altitude to the radius of the planet. So 3895 plus 640 is 4,535 kilometers. To calculate the orbital period, t is equal to 2 pi times the square root of, r cubed over g over m. So on my calculator, that would be 2 pi square root of 4,535,000 cubed divided by g divided by 3.89 times 10 to the 23rd power, enter. And I get an orbital period of 11,900 seconds. But to express that in minutes, divide that by 60, and I get 199 minutes. And yes, you lose points if you don't express the answer in the units that are requested of you. Number 4. A spaceship orbits Phi Cancri 2 in a period of 15.50 hours. Phi Cancri 2 has a mass of 5.48 times 10 to the 26 power kilograms and a diameter of 60,560 kilometers. Calculate the altitude of the spaceship above the surface of the planet. So we're given the diameter, and you should realize that the radius is going to be half of the diameter. So the radius of this planet is 60,560 divided by 2. You can almost do it in your head, is 30,280 kilometers. The period is 15.50 hours, but of course that needs to be expressed in units of seconds. So 15.50 times 3,600 seconds per hour is 55,800 seconds. Now we can solve for the orbital radius in Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed over gm, and we're rearranging to solve for orbital radius. R is equal to the cube root of gmt squared divided by 4 divided by pi squared. All right, so we're going to take open parentheses, alpha g. The mass is 5.48 times 10 to the 26th power times t squared divided by 4 divided by pi squared, and raise all of this to the inverse of third power. This will give us the orbital radius in meters. If I divide this by 1,000, this will convert it to kilometers. So the orbital radius, r, is 142,000 kilometers. But they are asking for the altitude above the surface. So knowing what the orbital radius is, if I subtract the altitude is equal to the orbital radius minus the radius of the planet. So if I go 142,000 minus the radius of the planet, which was 30,280 kilometers, the altitude h above the surface of this probably gas giant planet is 112,000 kilometers. Number 5. A space beacon orbits Nazi 6 at a speed of 2.31 kilometers per second at an orbital radius of 9,150 kilometers. Calculate the mass of Nazi 6. V squared equals gm over orbit radius r is what I would use. And in this case, rearranging to solve for the mass of the planet, the mass of the planet is equal to the product of the orbital speed squared times the orbital radius divided by the universal gravitational constant, as long as you use the right units. So into my calculator, I would type in 2,310 squared times 9,150,000 meters. Divide by universal gravitational constant, and I get a mass of 7.32 times 10 to the 23rd power kilograms. This concludes the debriefing on circular orbits homework 4.